SN2 reactions happen best on methyl type systems, and then they happen slower but okay on primary systems, and then it gets progressively worse to the extent that they don't happen at all on tertiary systems. By contrast, because SN1 reactions go through carbocations, and therefore carbocation stability matters a lot, what matters most for an SN1 reaction is how stable is a carbocation. And the answer for that is the more stuff, the better. So a tertiary carbocation is way more stable than a secondary carbocation, which is much more stable than a primary, which is nearly infinitely stable compared to a methyl, and that's then why a methyl carbocation basically never forms at all. But even if you back up to a primary carbocation is not likely for SN1. And then it gets better, where secondary is better than primary and tertiary is better still. And so the trends for SN1 and SN2 are precisely opposite, and that is because in an SN2 reaction you are actually colliding, and that displacement happens better with smaller things. But with SN1 you're trying to stabilize a carbocation, and carbocations are more stable when you have more stuff around them. Now, to illustrate why that is, you need to consider a methyl carbocation. I've drawn the carbon of the methyl and I've drawn the 3 hydrogens, but this is a methyl cation, which means that you have an empty orbital sitting right here. So this is going to be an empty p orbital, and since it is empty, then this carbon is a plus and locks an octet. This is obviously a very bad scenario because you do not want to have a plus on a carbon in general because it lacks an octet. So that's bad. With a methyl carbocation, there's nothing that can stabilize this. It just sits there like that. But now let's imagine an ethyl carbocation. So almost everything is the same, except now, in addition to having one carbon here, we have a methyl group over there. Does that change much? Well, actually it changes a lot. And the main reason why something changes is because right here you have a carbon-hydrogen bond that's contained in a sigma orbital. And at the moment, that sigma orbital is straight up and down, which is exactly where this carbocation empty p orbital is sitting. And what that means is this pair of electrons holding the hydrogen in place is lined up with this orbital, and therefore you can donate some electron density from that carbon-hydrogen bond into that empty orbital. The fancy term for that sort of through-space interaction is hyperconjugation. And if you remember an actual diagram for ethylene from earlier in the semester, then you would remember that this is exactly what a pi bond looks like. Now, with a pi bond, you have substantial overlap of both lobes of 2 p orbitals, and you're actually sharing a pair of electrons, which really is a strong scenario. This is nowhere near as strong. This is on the order of maybe a couple of kcals per mole, whereas a pi bond is more like 100 kcals per mole. So this is substantially weaker, and yet it's a substantial amount of stabilization that is simply not available in a methyl cation scenario. On the other hand, there is only one of these interactions happening at any one time, and this can rotate freely, which means that you can at any one moment have one hydrogen lined up stabilizing things. So this is better than that was, but it's not as good as having more stuff around it would be. So if having one hydrogen aligned the right way is good, having 3 different hydrogens all aligned the right way has to be even better. And so now, just drawing the main lobe for each of these hydrogens, carbon-hydrogen bonds that are aligned properly, what you can see is that at any one given moment, there are 3 hydrogens that can be donating in. And so if this was worth, say, 2 kcals per mole, then that would be worth, say, 6. And what we have here is basically only one hydrogen can be aligned at any one time, but here there are 3, so even when things are rotating through, the odds that something is always stabilizing that carbocation go way up. So this is a vastly better scenario than the methyl carbocation in the first place. But it is vastly better than even a secondary, and it's vastly better than a primary as well. What would be even better still? If we had a nearby pi bond, then you would actually have a resonance scenario, and that would stabilize things even more. And this would be a substantial improvement over carbocation stability as well. So not considered in this initial list is resonance itself. And the idea is that a tertiary plus resonance is going to be better than a tertiary was originally, and a secondary plus resonance is going to be on the same order of magnitude as a tertiary without resonance, and a primary plus resonance is going to be at least on the order of a secondary. So basically, having resonance shifts you over substantially, and that is because it can substantially stabilize the carbocation intermediate. Which should make sense. If you're looking now at the allyl cation that I drew here, what you have is a scenario like this where you have a cation at this point and you have an actual pi bond right there with actual p orbitals overlapping in all lobes with this right there. And in fact, though I've drawn it as localized here and a separate p orbital there, you know from MO theory that that's not the case. In fact, as soon as you create this allyl cation, what happens is you create 3 new orbitals, one where you can smear the electrons across the entire area, and that is vastly stabilizing. So again, a primary plus resonance is quite good a secondary plus resonance is really, really good, and a tertiary plus resonance is going to form very, very quickly. And that's even if you only have a single double bond nearby as the source of the resonance.